In our previous video, we defined several terms related to spherical mirrors. What are spherical mirrors? Mirrors in which the curved reflecting surface forms a part of a sphere are called spherical mirrors. Spherical mirrors can be of two types. One in which reflecting surface is curved inwards, they're called concave mirrors, and the others in which the reflecting surface is curved outwards, they're called convex mirrors. The center of the reflecting surface is called the pole. The center of a sphere of which they form a part is called the center of curvature. And the radius of that sphere is called the radius of curvature. Cp here is the radius of curvature. Note that for a concave mirror, the center of curvature lies at the front of the reflecting surface, whereas for a convex mirror, it lies at the back of the reflecting surface. Okay, I also told you that the midpoint of Cp is called the focal point of the respective mirror. The other name for it is principal focus. It's called so because it lies on the principal axis. Okay, let's just remove the convex mirror for a while and concentrate on the concave mirror for now. Now this focal point of a concave mirror is a little more than just a midpoint. It's also a point where all the rays of light parallel to each other as well as to the principal axis converge after reflection. Let's try to understand this statement in detail. Let's take the sun as our object. Why? Because I want only parallel rays of light to be incident on the mirror. And the rays of light from the sun can be considered to be almost parallel. But why? Being a sphere, sun emits light radially outwards. That is, rays of light travel outwards along the radius. But we know that the sun is at a very large distance away from the earth. Hence, the rays from the sun coming towards the surface of the earth are considered parallel. So our object, which is the sun, is present at infinity, and it's emitting parallel rays of light. We know that all the rays of light after being incident on any surface will follow laws of reflection. We see that after reflection, each ray is indeed following those laws. Angle of incidence is equal to the angle of reflection. And all the three lie in the same plane. Where are they going after reflection? Well, they are all meeting each other at the principal focus. Yes, they are all converging at the principal focus. And this is where the image of an object is formed. Yes, this is an image of the sun and it's a real image. Now, if you project this point of convergence on a piece of paper, the paper at that point will start getting hotter and will eventually catch fire. As the bulk of rays from the sun are all concentrated at one single point by this concave mirror, the temperature at this point rises. And it's too much temperature for a thin piece of paper to withhold. Similarly, instead of a sun, we can take any other object kept at infinity. And the rays of light from that object incident on the mirror will be parallel to each other. So we saw that if the rays of light are parallel to each other as well as to the principal axis, they will always converge at the principal focus. And this is true for any other object as well. Now I would want to mention one thing here, that this does not depend on the position of the object. Yes, it does not only work when the object is at infinity. No matter where the object is kept on the principal axis, if the rays of light incident on the mirror are parallel to each other as well as to the principal axis, they will always converge at the principal focus. What if the rays of light are parallel to each other but not parallel to the principal axis? Where will they go in that case? Let's find out what happens then. Suppose that the rays of light are incident on the mirror. As you can see, these rays are parallel to each other but not to the principal axis. These rays will be reflected in such a way such that the laws of reflection are obeyed. You see that here also all the rays are converging. But here the point of convergence is not the principal focus. Instead, it's a point above the principal axis. This point is called focus as all the rays are focused at this point. It's not called the principal focus because it does not lie on the principal axis. So we defined focus as a point where all the parallel rays converge after bouncing off from the reflecting surface of the concave mirror. It is the principal focus if it lies on the principal axis. And it will only lie on the principal axis if the rays of light are parallel to each other as well as to the principal axis. What if the light rays are passing through the principal focus? Yes, it means the light rays won't be parallel. Consider one light ray from a point on the object passing through the principal focus and is incident on the mirror. We know that this ray will be reflected according to the laws of reflection. Consider two more rays from different points of the object, both passing through the principal focus, incident on the mirror. After reflection from the concave mirror, we see that they all travel parallel to the first reflected ray. So what can we conclude from this? If the rays of light pass through the principal focus and are incident on the mirror, then after reflection, they travel parallel to each other. And this is true for any position behind the principal focus. But what if the object is kept at the principal focus? Well, in that case also, all the rays will travel parallel to each other after reflection. I want to discuss one important point before I end this video. In reality, every object emits rays of light in all possible directions. Or to be more specific, from any point on an object, infinitely many rays of light travel in all the possible directions. But then, where will the image of the object be formed? Is it formed on the principal focus again? In the coming videos, we will learn the characteristics of images formed by concave mirrors. We have already seen the characteristics of images formed by plane mirrors. The image is of the same size as the object, and it's also at the same distance away from the mirror as the object is. And the image follows left-right reversal. It means that the object's right is the image's left and vice versa. And lastly, the image formed by a plane mirror is a virtual image. So what about the images formed by concave mirrors? Do they have the same characteristics? You all must have seen the reflection of your face in a spoon. Spoon has two smooth surfaces, one curved inside and the other curved outside. However, it is not perfectly spherical. For ease of understanding, we can consider the reflecting surface which is curved inwards as a concave mirror. I will show you how the image appears, but using an actual concave mirror and not a spoon. So let's try and find out the properties of an image formed by a concave mirror. I will show you two views of the mirror, the front view and the side view. The side view is just to show the different positions where the object is kept, as it's difficult to do that in the front view. Okay, so let P be its pole, C its center of curvature, this line is the principal axis, and the F is the principal focus, also called focal point. Assume that initially the object is kept close to the mirror. I will make a table on the right with 3 columns telling us where the object is kept, the size of the image formed, and the nature of the image, that is, whether the image is virtual or real. So initially the position of the object is between F and P. What is the size of the image? We see the reflection in the concave mirror and the image is bigger in size. We see that it's enlarged. The dimensions of the image are greater than the dimensions of the object. So we say that when the object is between the principal focus and the pole, the image formed is enlarged. Also, is the image upright or erect? What about the nature of the image? Is it real or virtual? Yes, it's the virtual image. It appears to be formed behind the mirror. Where is the location of the image? It is a virtual image, so it does not have any location. It only appears to be formed in a location behind the mirror. But we will find that location in our next video using ray diagrams. For now, let's move this object away from the mirror and see how the dimensions and the nature of the image vary relative to the object. you will find that as I move this object away, its image gets even bigger. And when the object is at the principal focus, the image is huge. We say that when the object is at the principal focus, the image is highly enlarged. Is it a real or a virtual image? It is a real image. Since it's a real image, it's upside down. Or we use the other word for it, which is inverted. It is formed on the same side of the mirror as the object is. And believe it or not, the image is actually formed infinitely far away. When I start moving this object away from the focal point towards point C, the image is still enlarged, but the size is reducing. And what is the nature of this image? Yes, here as well, the image is upside down. It's a real image. When the object is at point C, the image is still real and inverted, but now the size of the object and its image is same. Yes, at this point, both the object and the image are of the same size. What next? If I move this object beyond point C, the image remains real and inverted, but now the size of the image is actually smaller compared to the size of the object. So we say that the image is diminished. This is also a real image. As the objects keep moving beyond C, the size of the image keeps on reducing. What if the object is placed at infinity? Well, if you remember that in our previous video, we saw that the rays of light parallel to each other as well as to the principal axis will converge at the focal point. And in that example, our object was the Sun. Sun is at a very large distance away from the Earth, and hence we consider the rays of light from it reaching the surface of the Earth to be almost parallel. The image of the Sun will be formed at the principal focus. Similarly, if any object kept infinitely far away from the mirror on the principal axis, all the rays from it can be thought of as travelling parallel to each other. After reflection, they will all converge at the focus. And the image of that infinitely far away object will be formed at this point. Yes, this is a point-size image. It's a highly diminished image and it's also a real image. Take a moment and go through the properties of images again. From this table, you can see that the image is virtual only when the object is kept between the focal point and the pole. Otherwise, the image formed is always a real image. In the next video, we will find out the position of these images using ray diagrams. Till now, we've only been looking at the properties of an image formed by concave mirror. However, there is one more type of a curved mirror. Do we know what it's called? Yes, a convex mirror. So what is a convex mirror? A mirror whose reflecting surface is curved outward is called a convex mirror. The question now is, how does an image formed by a convex mirror look like? Without further ado, let's find that out. We will draw a table on the right just like we did for a concave mirror. Here is a convex mirror. Suppose an object is kept at a finite distance away from it. Look carefully at its image formed. Can you orally tell me the properties of the image by just looking at it? First of all, we conclude that the image is smaller in size compared to the object. This is very clear. The image is diminished. The light rays seem to come from the point behind the mirror. But obviously, we know that no image is formed there. So this is a virtual image. Also, it's an upright image. Remember that every virtual image is an upright image. What if I move the object towards the mirror? If I move the object towards the mirror, the size of the image keeps on increasing. But the size of the image with respect to the object is always smaller. What will happen if I move the object away from the mirror? As I move the object away from the mirror, the relative size of the image keeps on reducing. Also, at any finite distance away from the mirror, image formed is always a virtual image. You know what's coming next, don't you? Yes. What if the object is infinitely far away? Well, in the case of a concave mirror, when the object was infinitely far away, the image was formed at a single point. It was real, point-sized, and a highly diminished image. Point-sized means that the whole image of the object is formed at a single point. Here too, the same thing happens. Image formed is indeed point-sized. But here, the image is a virtual image. So when the object is kept at infinity, the image formed is virtual, point-sized, and highly diminished. Notice that even though the object is kept at infinity, the image is not at infinity. It is at a finite distance behind the mirror, even though the object is infinitely far away. In fact, this is the maximum distance at which image can be formed. Image in a convex mirror cannot be formed behind this point. We will now represent the image formed by a convex mirror using ray diagrams. Let's try to draw a ray diagram for this case first. This is when the object is at infinity. Our object will be the usual arrow, and suppose it's at infinity. Now if you remember, I told you that the rays of light coming from the object at infinity are considered to be parallel to each other. And we know that two rays are sufficient to draw a ray diagram, so we will take any two parallel rays striking the mirror. These rays will be reflected in such a way that laws of reflection are obeyed. We notice that the rays are diverging after reflection. And when we extend these rays backwards, they meet at a single point, which is the principal focus in this case. What does this imply? When we are looking at the image of an infinitely far away object, it appears to be formed at this single point behind the mirror. If the parallel rays are traveling in this direction, the image is still formed at a single point, which is different than the principal focus. We call this point focus, as it does not lie on the principal axis. What now? Now let's keep the object at a finite distance from the mirror and try to represent the image formed for this case using a ray diagram. So how did we proceed? We only need to take any 2 points on the object which is represented by this arrow. Find out the image of these 2 objects' points first by drawing at least 2 rays emerging from each point. After reflection, all these rays will follow the laws of reflection. When we extend these rays backwards, we get our image locations. I repeat again that this is not a real location in space. It's only a location where the image appears to be formed. I want to pause here for a moment to tell you the reason exactly why I chose these 2 rays only. One parallel to the principal axis and the other directed towards the focal point. Yes, these are not random 2 rays. I chose them on purpose. Well, if you remember, when we were talking about the ray diagrams for images formed by concave mirrors, we saw that the rays which are parallel to the mirror will always pass through the focal point after reflection, and the rays which pass through the focal point will always travel parallel to the principal axis after reflection. There, we had only used these 2 rays to draw all of our ray diagrams. But in convex mirrors, we know that the rays cannot pass through the focal point as it lies behind the mirror. But if I direct the incident ray towards the focal point, then after reflection, it travels parallel to the principal axis. Yes, any ray which is directed towards the focal point, it will travel parallel to the principal axis after reflection. Also, if the incident ray is traveling parallel to the principal axis, then after reflection, it will look as if it originated from the focal point. For instance, here all these reflected rays seem to be coming from this focal point. With this bit of knowledge, let's jump back to where we were initially. Now I think you understood the reason behind my choice of these 2 rays. Okay, so let's quickly join these image points to get the complete image of the object. If we measure the length of the object and the image, we will find that the object's size is greater than its image. So we say that the image is diminished. Also, one more important thing that I must say is that the image's distance from the mirror is not the same as the object's distance from the mirror. If you remember, when we were discussing plane mirror images, the virtual image distance and object distance from the mirror were the same irrespective of where the object was placed. Here, even though it's a virtual image, it does not follow that property. So, these two are the ray diagrams representing the image and its properties. When the object is infinitely away from the mirror, we get a point-sized image at the focal point. And as we keep moving the object towards the mirror, the size of the image keeps increasing and it appears to be coming closer to the backside of the mirror. In the next video, we will see some uses of concave and convex mirrors in real life. In videos, we have been looking at the properties of images formed by convex and concave mirrors. Now the obvious question echoing in everyone's mind must be that in reality, where do we take advantage of these properties? Where do we use convex and concave mirrors? Let's study the uses of a concave mirror first. Have you seen solar heaters? Solar heaters are the devices that use the energy from the sun to heat something. It is the most common device which uses a concave mirror for its function. We already know that the rays of light coming from the object kept at infinity converge after reflecting from the surface of a concave mirror. Here, the sun is very far away and hence the rays of light coming from it are parallel near the Earth's surface. These parallel rays after reflection converge at a point called focus. This focus is a very hot location in space as all the reflected sun rays are concentrated at this point. If we bring a piece of paper at this point, it will quickly catch fire. Now we can use this property of concave mirrors to cook food or heat up liquids. All we need to do is place the container on this stand which is present at or near the focus. It will heat up after some time. You can even make a roti or a papad on this. Where else in the world do we use these types of mirrors? We can use concave mirrors to view the objects which are very far away from us. Yes, I am talking about the astronomical telescopes. How is a concave mirror used in a telescope? When the parallel rays of light from the distant star enter the telescope, they fall on the concave mirror which is placed on the opposite side. This concave mirror then converges all the light at a focal point. So the image of the star is formed at this point in space. The secondary mirror is then placed near this focal point. It's kept like this so that it can reflect the light upwards towards the eyepiece. And the eyepiece has a lens which then magnifies this image. This way we are able to see an enlarged image of a faraway object. This particular type of telescope is also called the Newtonian telescope as it was Isaac Newton who first came up with this concept. Which is the lens used here near the eyepiece? The lens used here is a convex lens or converging lens. Well, we haven't really studied about lenses yet. Don't worry, we will come to that very soon. First, let's continue to study the applications of curved mirrors. If you remember, in the previous videos, we talked about this mirror which can be found in bathrooms. Many men use it for shaving purposes and quite a few women use it for beautification. Yes, this is also a concave mirror. And it must be very obvious now as to why we use it here. Due to the enlarged image, it gives a better view of our face. One more place where concave mirrors are used is the headlights of automobiles. And why do we use headlights? Headlights help us to see things in front of us in dark or in dim light. And using the headlights, we would want to see the things which may be at a sufficiently large distance ahead of us. So how do we achieve that? Let me quickly review something about concave mirrors. We know that when the object is kept at the focal point, the light rays from the object after reflection travel parallel to each other for a long distance. So if we keep a light source, say a bulb, at or near the focal point of a concave mirror, then almost all the rays from the bulb after reflection will travel in one direction. If the same concept is used in the headlight of a car, it will give us the distant view of the road ahead. This solves our purpose of viewing cars or things which are at quite a distance away from us. However, in reality, we don't really want all the rays to be travelling parallel after reflection. That is, we also want some of the rays to travel a bit sideways. We not only want to see the road ahead, but also the things along the sides. This will help us see the vehicles coming from the other side of the road in opposite direction. So for that purpose, we use what we call as deflectors. They deflect some of the light rays by smaller degrees. Now that we're talking about a car, let's discuss its view mirror. What is the use of the side view mirror of a car? Is this also a concave mirror? Watch our next video to know more.